Coronavirus, you are my kryptonite. Apparently, what I'm good at, the only thing I'm good at, is standing in front of an audience and speaking excitedly. But now there is no audience. There is an empty room. I am alone in the dark, trying to say something to this unblinking recording eye. Let's punch through anyway. Hello, and thank you for inviting me to this wonderful workshop on cosmological correlators. I don't think I've ever worked on cosmological correlators as such, but I have some adjacent ideas that I'm very happy for this opportunity to run past you. Well, some of what I'd like to discuss is partially contained in these recent and upcoming papers with Adi, Nico, and Emil, who I've collaborated with here as students at OIST. Now, my personal obsession is de Sitter space, and I want to understand quantum gravity in de Sitter space. That is hard. So we must make sacrifices. I make two. The first is that I ignore Big Bang cosmology. So if we're going to talk about de Sitter, we'll start from talking about pure de Sitter that has both a future de Sitter conformal infinity and a past one. The second sacrifice is that in order to have a concrete microscopic model, one has to leave general relativity behind, as well as string theory that contains it. So our string theorist friends are famously very good at doing quantum gravity with negative cosmological constant using ADS-CFT, and there is one precious golden example of ADS-CFT which doesn't seem to obviously break upon continuing to positive cosmological constant, and unfortunately that example does not have string theory and GR as a limit in the bulk, but instead this cousin of string theory and supergravity called higher spin gravity or Vasiliev gravity, while the boundary theory is essentially the simplest imaginable one, which is a free vector model. Okay, and so this makes the one known microscopic DS-CFT. Given a model of DS-CFT, by the gods, one needs to ask, what does it calculate? And the canonical answer has been given to us by Maldacena in his seminal paper on non-Gaussianities in inflation, where he says that the partition function of the CFT living here at future conformal infinity defines the Hartle-Hawking wave function, or if we descend from quantum gravity jargon to quantum field theory jargon, the Bunch-Davies vacuum wave function of the theory in de Sitter. Okay. And this is precisely the sort of thing that we like to calculate when thinking about inflationary cosmology. Okay. There is some de Sitter space, we calculate its wave function at conformal infinity, knowing all the while, wink wink, that in fact this is not really future conformal infinity, that the de Sitter phase ends. We enter something like standard Big Bang cosmology, and these correlators or wave function that we calculated from our CFT become the input for what will be observed in the future as the CMB sky. Now, here is where I depart from the conventional story, which is I would like to really insist that we not talk about the inflationary de Sitter, if only for the next 20 minutes. Okay? People talk about it enough, sometimes forgetting that it's hypothetical. But I'd like to talk about the observed fact that we currently have what seems to be a small positive cosmological constant, and there is nothing except the preferences of some theorists to prevent us from extrapolating it into the future and concluding that we live in a true future asymptotically de Sitter, whose conformal infinity will never become observable. All right? So if we live in a true de Sitter spacetime, then the maximal observable region of it will be determined by where we are as an observer inside this spacetime. In particular, at which point of past conformal infinity we are born, and at which point of future conformal infinity we die. Okay, so the light cone of this point makes a past horizon. We can only prepare measurements, send out probes, and so on to the future of this. The light cone of this point is our future horizon. We can only receive back signals to the past of this. Right? So the actual physically accessible region of space-time is this intersection here, which I would like to call the causal patch of an observer, but unfortunately it already has a name, and it is called the static patch of de Sitter space. Okay. So the obvious, if you will, observable in a de Sitter universe is not a partition function or correlators at conformal infinity, not because those are not the nicest things to calculate, but simply because they're not observable. But rather the next best thing would be correlation functions on the boundary of an observable patch, namely the future and past horizons here. So what we might call the S matrix for this de Sitter observer, how initial data on the past horizon evolves into final data on the future horizon. So my interest becomes, in the first place, to calculate this observable, this de Sitter S matrix, for the theory of quantum gravity at hand, for higher spin theory, somehow cleverly using what we know about its holography at this unobservable conformal boundary. But taking a step back, it is also interesting to ask this question for more ordinary, more familiar field theories. And to keep things simple and closer to the higher spin theory example, let us say theories of massless fields. Massless scalars, perhaps interacting, spin 1 gauge fields, perhaps with Yang-Mills interactions, perturbative GR to the extent, to the order at which it makes sense. So what is known about the S matrix of different field theories in a de Sitter static patch? Now, this is where my first question to you enters. To the extent of my knowledge, absolutely nothing is written by mankind about this seemingly very basic question in mathematical physics. To the extent that the linearized version of it, the free field version of it, ended up being published by us last year in the 2019 paper we had over here. So please tell me whether or not I'm crazy, whether in fact something has been done with this problem that I'm not aware of. So assuming that nothing has, we can ask why. And at least part of the answer would be that the symmetry of this problem is kind of dauntingly low. Right? So the symmetry group of the sitter space itself is, of course, SO4, 1. But the choice of observer, the choice of static patch, breaks it down to the SO1, 1 of the observer's time translations times SO3 of spatial rotations. So you have at your disposal frequencies in time and spherical harmonics. That's not much. Okay? That means you don't have momentum states to play with, and spherical harmonics stop being fun fairly quickly. So here I would like to introduce my very basic trick for how to think about this problem. And the statement is that we can take the problem's square root. We do in 2 steps. First, instead of asking about these halves of the cosmological horizon, right, this actually observable half of the past horizon and this half of the future horizon, we can ask about the entire thing. So given initial data on this entire hypersurface of the initial horizon, how would it evolve onto this entire final horizon? Now, clearly, if we know the answer to this question, then we can always cut in half in the end and obtain the answer to the original one. Now, when I say clearly, I always lie. And in this case, we are running the risk of introducing some important effects at this boundary. Okay, important in the sense of this whole burgeoning industry of soft or infrared or edge degrees of freedom that may end up being very important in quantum gravity, and I will return to this issue towards the end. But up to that, okay, if we care about the hard part of the de Sitter S matrix, then we are within our rights to ignore this boundary issue and swap the half horizons for these entire horizons. The next step of the trick is to suddenly change the question. As you can see, the board has magically suddenly changed. Instead of thinking of a static patch trapped between two horizons, let's talk about the much nicer Poincare patch of de Sitter space, which is enclosed between a single cosmological horizon in the past and the future conformal boundary. Okay. The metric of the Poincare patch takes this very friendly conformally flat form, which is manifestly symmetric under not just 3D rotations, but also 3D translations and dilatations. So in particular, we now have momentum states, plane waves, to work with. Okay? And the problem of transition amplitudes between the conformal boundary and the horizon becomes just the problem of evolving fields from z equals 0 in Poincare coordinates to z equals infinity. Now, why is this problem relevant to our original one? Because if we know how to relate conformal infinity to one horizon, then we know how to relate it to any other horizon. Right? They are all related to each other by the de Sitter group, or the conformal group of the boundary. So if we know how to relate the fields on a single horizon to this global structure on the boundary of the entire space-time, then by doing it twice to two different horizons, we can end up with the actually observable relationship between fields on one and fields on the other. For free massless fields, this procedure can be beautifully carried out, and in a smarter way than what I've actually described here now, with the role of space-time replaced by spinor and twistor space. The idea is that to describe the plane waves of free massless fields in Poincare coordinates, whether it be on the boundary or on the horizon, we can use spinor helicity variables. Right? So taking the 3D momentum with respect to spatial coordinates, writing it as the square of some SU2 spinor, and using the phase of the spinor to encode helicity. So we can encode the states of free massless fields as functions of this spinor helicity variable and its complex conjugate. Now, the statement for how to calculate the S matrix from one such horizon or set of Poincare coordinates to another is that we simply need to Fourier transform with respect to the spinor coordinates, so that the spinor helicity function with respect to a second horizon is given by Fourier transform of this form. Now, the reason why this is true, or the place where the square-rooted problem is hiding, is that you can convince yourself that a Fourier transform with respect to just one of the spinors, if we go in 2 steps, first Fourier transforming lambda bar into mu bar, and only then lambda into mu, then, well, this is the spinor helicity function with respect to one horizon. This is the spinor helicity function with respect to the second horizon. Then this is the twistor function, the Penrose transform, okay, that describes the free massless field solution in a way that is completely covariant under the full de Sitter group. Okay, so just as in space-time, we said we can go from one horizon to another by first going to the global structure on the conformal boundary. So here we can go from one spinor helicity description to another by first going through the global description in terms of twistor functions, okay, where each of these steps is more symmetric than the whole. Okay. This is the essence of our 2019 paper. Now, for interacting massless theories, with the exception of higher spin gravity, but for pedestrian ones, like interacting scalars, Yang-Mills, GR, I'm not yet smart enough to think at this level. So back to space-time it is. Back to the paradigm that we want to evolve fields from one horizon to another, but secretly the answer to that hard-looking question is contained in its easier square root, which is the evolution from the conformal boundary to a single horizon. So perturbatively, that means calculating Witten diagrams that have some of their external legs here on the boundary and some here on the horizon. Now, in our upcoming work with Emil, we have simply done that for some simplest cases at the first non-trivial order, with the results that Yang-Mills is nicer than interacting scalar, while GR is intermediate between the two. So here comes my second question to you fellows as a community. I feel crazy. I'm missing something because the cosmological literature is vast, but I can't seem to find a clear place where this exact question, again, a very basic question in mathematical physics, is studied, just as for the original one about the static patch. Has someone calculated these transition amplitudes where not all legs are on the boundary, but some are on the horizon? Please help me out. I feel like it's impossible that I'm the first person doing this, but I'm also not aware of the counterexample. Let me share with you the very peculiar place I find myself in when I try to apply these ideas to my main case of interest, which is higher spin gravity. First, let us frame the problem of interacting fields in de Sitter in a slightly strange way. Well, we have some final data at the conformal boundary and some initial data at the horizon. They are non-linearly related to each other. But for each of them, we can pretend that they were the boundary data for free massless field theory. Okay? In free massless field theory, we can translate from the fields on any old hypersurface and any old coordinate system into the Penrose transform into a twistor function. So for the final data on the boundary, we can pretend that it is data for free fields and encode it as some twistor function. And similarly, for the initial data on the horizon, we can pretend that it is data for free fields and encode it as another twistor function. The statement that the theory is interacting, that the evolution between boundary and horizon is not the same as for free fields, is simply the statement that these twistor functions are not equal to each other. Right? That there is instead some nonlinear relationship between them. And what this nonlinear relationship might be will depend on the symmetry of the problem. Now, what is so bizarre about the case of higher spin gravity is, well, it has this vast constraining symmetry. It extends the space-time symmetry of GR into this infinite dimensional higher spin group. And it appears that while it allows non-trivial, non-linear relationships between boundary and horizon, it does not leave room for dependence on the choice of horizon. So the mapping of the boundary final data to some other horizon must be literally equal in the twistor function language to that of the first horizon. So the twistor functions of the two horizons end up being equal, which, coming back to space-time language, means that the fields on the two horizons are related by the free field S matrix. Even though we're in the interacting theory, and even though there is a non-trivial, non-linear relationship between either one and the fields on the boundary. So the statement appears to be that the S matrix in the Sitter space of higher spin gravity is unaffected by interactions due to its symmetry structure. But I refuse to believe that that is the entire story. So I look for loopholes. And the loophole that I can see is coming back to the earlier discussion from when we were cutting the horizons in half and being cavalier about the boundary effects, edge effects, infrared, soft, zero frequency effects that we might be losing then. And I suspect there are other places where I'm not keeping track of infrared effects correctly. So the conjecture then becomes, the interactions of higher spin gravity manifest in the S matrix of a de Sitter observer, but only in the infrared soft sector. Now, my third question to you wonderful people. Is there one among you who would be interested to collaborate on zero frequency effects in cosmological correlators? I have here a theory where I claim that they are the only effects, that they contain all the dynamical content. And in the process, we end up investigating a working model for quantum gravity with positive cosmological constant. It will be fun. Thank you very much.